Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video describes ways to interpret histograms. Let's get started. Histograms may be easy to make, but we don't make them for their cuteness factor. We make them to help us get our arms around the data and understand the data better. Typically, we like seeing a normal distribution because, as we'll learn later in the course, we've got lots of tools in our stats toolbox for working with normal distributions. Remember that the normal distribution has that characteristic bell shape to it. Each half of the graph mirrors the other, and that's essentially what we see when we examine the shape of the distribution in this histogram here. Now, one of the advantages you get in StatCrunch with creating a histogram instead of a frequency distribution is that you have the option to change the width of the bins in which your data are collected. You do this inside the options window by entering your desired bin width into the field next to width under bins. Now, increasing the bin width will decrease the number of bins in your histogram, and decreasing the bin width will increase the number of bins. Let's see what effect this has on our ability to analyze and interpret a histogram. Let's examine the population of straw length measurements we saw earlier, but this time we'll make separate histograms for bin widths so we can see what effect changing that has. The default bin width is 10, and we already have that histogram, so let's make two more, one with a bin width of 15 and the other with a bin width of 5. Now, feel free to pause the video here and make these for yourself in StatCrunch. Okay, I hope you were able to get histograms that look like these here. If not, go back to StatCrunch and try again. Now, notice how the shape of the underlying distribution appears different with different bin widths. Typically, you're not going to change the bin width, okay, because StatCrunch will automatically use the width that should give you the optimal number of bins. Well, you may wonder, why does that matter? Well, if you stray too far from the optimal number, the resulting shape can obscure important features you would otherwise see. For example, how many populations do we have in our data set? Well, if I look at what we get here with the default value, there's a gap here, indicating the presence of two distinct populations. If I increase the number of bins by decreasing the bin width, okay, I can still see the gap indicating two populations. But look over here what happens when I decrease the number of bins by increasing my bin width. Now the gap is not there. You might argue that 2 is a really low value, and so there might be a gap there, but you can't say it as definitively as with the other examples, because here the number of bins is obscuring the detail indicating two populations. Let's go ahead and examine the histogram with the optimal number of bins. Now, to read the histogram, notice that not every category or bin is labeled, and the numbers you do see appear offset. That's a common way of abbreviating the horizontal axis. Just remember that each category includes the number, or the marker where there's not a number, to the left. So this first class, or bin that has 10 counts, okay, starts at and includes 50, because 50 is halfway between 40 and 60. And the next column, okay, that has 6 counts to it, this begins and includes 60. So 60 belongs in this column here. 70 would then belong in this column here. Now, so on and so forth. So what can this histogram say about the following? What is the approximate number of straws with a length greater than 100 millimeters? Well, I hope you said 8. Okay, here we have 3 columns. Their counts are 3, 2, and 3, respectively. So the total number of straws that are greater than 100 is 3 plus 2 plus 3, which is 8. Now, is that what we would expect from what we know about the population? Yes, it is. If you'll remember, one group of 4 straws was cut in half, making 8 straws that would be significantly longer than the straws from other groups that were cut into thirds or quarters. Okay, what here is the class width? Okay, you can look here and see the class width is 10. Okay, just take any 2 adjacent markers and subtract their values. So you could take 60 minus 50, or you could take 70 minus 60, but just any 2 adjacent markers will give you the same number. Now, what are the approximate lower and upper bounds of the first class? Well, it's going to be 50 to 60, including 50, but not including 60. Note, this square bracket here, okay, means 50 is included in the data set, and the parenthesis means 60 is not included in the data set. So the set of possible values in this class include everything starting at 50 and on up at 2, but not including 60. Are there any outliers in the data set? An outlier would be a value far removed from the bulk of the other data values in the set. No, there's no outliers here. Everything's pretty much together, so no outliers. Is there a gap? Yes, we've already seen that there's a gap here. We've already established that. Now, what might explain the presence of the gap? Well, as we've already discussed, there are 2 distinct populations here. One population has straws that are considerably longer than the other population. Before we finish, let's consider an important characteristic of a data set. Skewness is a measure of how much the data has shifted away from making a symmetrical bell curve shape. Data can be skewed either to the left or the right. Now, if you were to ask my friends in industry, they would say that when the bulk of the data is shifted towards the right, that means the distribution is skewed to the right, and vice versa. However, pure statisticians don't see it that way. They're looking not where the bulk of the data goes, but where the larger tail is when the data shifts. So when there's a longer tail on the right, then the distribution is positively skewed or skewed to the right. And when the longer tail appears on the left, then the distribution is negatively skewed or skewed to the left. Now, that makes absolutely no sense to me. I don't care about larger tails. I want to know where the data is going. So I tend to think in those terms. But hey, Mark Twain once said, common sense ain't so common. And that's definitely true here. So to evaluate skewness, look for where the larger tail is in your skewed distribution. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.